Cosmology Supplement 4, Cosmic Horizons, the Hubble Distance, and How Ancient Light Reaches Us. Hello, welcome to this supplemental video on the particle horizon, event horizon, Hubble distance, and how ancient light reaches us for the Expansion of the Universe course. The lecture script is available at a link given in the description of this video. In this supplemental video, we will consider light or other radiation that has been traveling the expanding universe for a long time and is reaching us now. We will also consider which light will or won't ever reach us in the future. We will learn the Hubble distance, the cosmic particle horizon, the observable universe, and the visible universe. We will learn how light from distant galaxies reaches us, and when it will never reach us. This video consists of 6 parts: the cosmic particle horizon, the Hubble distance, cosmic event horizon, how ancient light reaches us now, how light reaches us in the future, proper distance and luminosity distance versus redshift. The description of the video includes links to the individual sections. The basic concepts are straightforward, but how the values change with time can be confusing, especially because expansion has transitioned from decelerating to accelerating. This is the longest and most technical of the supplemental videos. I considered splitting this into multiple videos, but this material is all related and at the same technical level. Some of this material goes beyond a typical introductory cosmology course, even though they should cover how light reaches us. I encourage you to pause the video and think about the results, at least after each section. After watching the video, I encourage you to rewatch it to solidify your understanding. To simplify the results, we assume a flat universe, zero curvature, and constant dark energy density. Our universe with radiation, matter, and dark energy that started with a hot Big Bang, that will continue to expand and never contract, and is expected to end in a big chill. We will be considering very large distances from ourselves, distances from here, from the Milky Way galaxy. Some distances will be the distances from us to some imagined galaxies very far away. So far away that gravitational attraction to the Milky Way can be ignored, and the galaxies are coasting with the Hubble flow of the expansion of the universe. Some distances will be to events that preceded galaxies. We will consider distances now at the present time, but also distances as they will be at some future time or were at some past time, but always distances from our Milky Way. Let's assume that we have available to us the function a of t that is the scale factor of the expansion of our universe as a function of time. For all time after our Big Bang origin, t equals 0. The time now is represented as t sub 0. The scale factor function has been scaled such that the scale factor at the present time is 1. We are only considering an expanding universe, so a of t is monotonically increasing, has gone from 0 in the beginning to 1 now, and will be larger than 1 for the future. We won't need to know the specific scale factor function for this video, but I used it to calculate these results. Part 1. The cosmic particle horizon. First, we will cover the cosmic particle horizon and the observable universe. Our universe had a beginning, the hot Big Bang. Time as we reckon it began with the Big Bang. If there was a universe before our Big Bang, ignore that for this video. Actually, we're going to take time being 0 at the end of cosmic inflation, around 10 to the minus 33 seconds after the Big Bang. This will simplify matters without hurting our conclusions, but these results do not apply for the cosmic inflation period. It is believed and assumed that the speed of light in vacuum has been constant at its present value at least since the end of cosmic inflation. Cosmologists use the term radiation for particles and waves that travel at or very close to the speed of light in vacuum as they traverse the vast space of the universe. Electromagnetic radiation, photons of light, microwaves, etc., travels at the speed of light. Gravitational waves travel at the speed of light. Neutrinos emitted in the first second of the universe have traveled at close to the speed of light for much of the age of the universe. It takes radiation time to travel a distance. Since our universe had a beginning and has an age now, we can only see radiation from a finite portion of our universe from the past. That finite portion is called our observable universe. I will make a distinction for light later. Let's consider radiation emitted at time t sub e, traveling the expanding universe and arriving here and detected at time t sub d. For radiation emitted at time tce, traveling the expanding universe and arriving here and detected at time t sub d, the cosmic particle horizon at time t sub d is the proper distance, the actual distance at a given time, given by the right-hand side. The scale factor at time t sub d times the speed of light times the time integral from emission t sub e to detection t sub d of 1 over the scale factor function of time. We will call this capital L sub capital PH, though I don't think there is a standard notation. Don't worry if you're not familiar with integrals or this expression. We will give distances in megaparsecs. 1 megaparsec is 3.24 million light years. In the main course, we considered cosmologists' current standard cosmological model, which gives scale factor A of t and the current age of the universe. I used these to calculate the following results. However, take these numbers as representative for educational purposes, with at most 10% precision and accuracy. Remember, the Hubble crisis is not resolved at present. The cosmic particle horizon now for radiation emitted after the early, brief cosmic inflation epoch is about 14,200 megaparsecs, or 3.2 times the current Hubble distance. This is the proper distance from us now of the original emission points where we would just now be receiving unimpeded radiation that was emitted after cosmic inflation completed. This is the current radius of the observable universe. It serves also for when neutrinos decoupled from matter 1 second after the Big Bang. In the future, cosmologists might be able to detect cosmic gravitational waves from the early universe or cosmic neutrinos emitted 1 second after the Big Bang. Our current observable universe was about 5.6 meters in diameter 10 to the minus 33 seconds after the Big Bang, when cosmic inflation completed. We integrated back to the end of cosmic inflation. Had we integrated back to the beginning of cosmic inflation, we would have gotten an appreciably larger cosmic particle horizon. See the main course section on how cosmic inflation solves the horizon problem. However, there were no photons or neutrinos during cosmic inflation, and the value that we got above is what we want. We could as well have integrated back to 10 to the minus 12 seconds after the Big Bang and would have gotten the same number. The earliest light we can ever see is the cosmic microwave background, emitted 380,000 years after the Big Bang. The light horizon distance now for light emitted at CMB last scattering is about 13,900 megaparsecs. This is the current radius of the visible universe, 2% smaller than the observable universe. Our current visible universe was about 25 megaparsecs in diameter when this light was emitted at CMB last scattering. The light horizon distance now for starlight emitted by the first stars as early as 50 million years after the Big Bang is about 12,140 megaparsecs, smaller than the visible universe. We can use the scale factor to determine the proper distance at the time of emission if we want. As we move the arrival detection time forward into the future, the horizon distances increase because the integrand is positive and because the scale factor increases with time. However, when we reach exponential expansion, the integral saturates at maximum values because the scale factor in the denominator increases so rapidly. But the scale factor in front of the integral continues to increase. This plot is the cosmic particle horizon distance divided by the scale factor in megaparsecs versus time in billions of years from 0 to 140 billion years after the Big Bang. This is the integral times the speed of light. The cosmic particle horizon moves outward faster than galaxies moving with the Hubble flow. As expansion continues, we see more of the early stars and galaxies, more of the cosmic microwave background, more of the early cosmic neutrinos, and more of any early gravitational waves, but dimmer and more redshifted. You can see the saturation when we get to exponential expansion. The final values for the horizons will be approximately 19,200 megaparsecs times the scale factor for neutrinos and gravitational waves, 19,000 megaparsecs times the scale factor for cosmic microwave background light, and 17,200 megaparsecs times the scale factor for light from the first stars, assuming a flat universe, constant dark energy density, the current estimates for cosmological parameters, and no mistakes on my part. So, 100 billion years from now, we will be able to see 35 to 40% further of early gravitational waves, cosmic neutrinos, cosmic microwave background, and early stars, galaxies, and quasars than today, though much dimmer and more redshifted due to continued expansion. You can skip this equation, but it turns out that the rate of change of the cosmic particle horizon with respect to the detection time equals the speed of light plus the particle horizon distance times the Hubble parameter. Here is a graph of the derivative for the first 30 billion years of the universe. The derivative is twice the speed of light in the early radiation-dominated universe, where the cosmic particle horizon and Hubble distance, which we cover next, are equal. The derivative increases with time and scale factor as radiation gives way to matter, and later, matter gives way to dark energy, and is infinite at infinite time in the exponentially expanding universe. The cosmic particle horizon recedes faster than the speed of light and faster than the Hubble distance recedes. As the universe ages, we see more of it, more of the early universe, more of the early stars and galaxies, more of the cosmic microwave background, etc. But the cosmic microwave background is already remarkably uniform in all directions. How this can possibly be is called the horizon problem. In the main course, we covered that cosmologists believe there was an early, brief, but important period of extreme, faster-than-light cosmic inflation in the early universe, such that all of our universe that is within our far future particle horizon was in causal contact and thermal equilibrium before cosmic inflation. This completes the section on the cosmic particle horizon. Part 2. The Hubble distance. For every distance we consider at a time different than now, there are two different but related versions of that distance. We will use the proper distance, d sub p, the actual distance across space at the time of interest. For two galaxies extremely distant from one another, both galaxies are flowing with the Hubble flow of the expanding universe, and any peculiar motion due to nearby gravitational attraction is generally less significant. The proper distance between the two galaxies increases with time proportional to the scale factor A of t as the universe expands. That is fairly easy to visualize. Take a galaxy that is 1,000 megaparsecs from us today, scale factor 1. When the scale factor reaches 2, about 11 billion years from now, the proper distance between that galaxy and us will be 2,000 megaparsecs. There is also the co-moving distance. We will not use the co-moving distance in this video, but it is necessary to derive some results. If you are reading some article and you see co-moving distance, you will need to learn the distinction between co-moving and proper distances, which we will not cover. We will call the time derivative of the proper distance due to expansion the recession velocity v sub p. This is the recession velocity of a given galaxy at a given proper distance from us. It turns out that this equals the Hubble parameter, h of t, times the proper distance at that time. In the main course, we learned how the Hubble parameter, h, varies with the energy densities of the components of the universe. Those energy densities vary with the scale factor, A, of t, which varies with time. In this supplement, we will only handle a universe that continues to expand forever, not contract. We will restrict kappa in the curvature term on the right to be 0, such that the curvature term is 0, a flat universe. The remaining 3 terms are non-negative, and the scale factor A of t will increase monotonically with time. We will restrict W for the dark energy term to be W equals -1. This makes the exponent in the dark energy term 0 and the constant dark energy density, and this universe ends in a big chill, not a big rip. Under these restrictions, the Hubble parameter will decrease monotonically with the scale factor and with time. For constant, non-zero dark energy density, the Hubble parameter will tend to a fixed positive value characteristic of the exponential expansion at large scale factor in the future. So the recession velocity is the product of the Hubble parameter, which decreases with time, and the proper distance to some galaxy, which increases with time. So we need to determine whether the recession velocity increases or decreases with time. We will call the time derivative of the recession velocity due to expansion the recession acceleration, a sub p. It turns out that this equals the proper distance times an acceleration term that we covered in the main course. In the main course, we saw that radiation dominates the early universe and the expanding universe decelerates. At a particular scale factor, matter dominates and the expanding universe continues to decelerate. Then at a higher particular scale factor, dark energy begins to dominate and the expanding universe accelerates. For the case we are interested in, the expansion will continue to accelerate forever. $6.14 billion years ago, when our universe was 7.63 billion years old, at scale factor 0.61 and redshift z 0.64, the expansion of our universe stopped decelerating and began to accelerate. This means that the recession velocity, always positive, between some distant galaxy and us, was decelerating with time from the Big Bang till the inflection time, was increasing after the inflection time, and will continue to increase with time and scale factor forever, though slowly. We will come back to this inflection time shortly. The Hubble time is 1 over the Hubble parameter, so the Hubble time will increase monotonically with the scale factor and with time. Multiplying the Hubble time by the speed of light, we get the Hubble distance at a given time. We will call this capital D sub capital H, though I don't think there is a standard notation. The Hubble distance increases monotonically with time for the conditions we're assuming. The blue curve is the Hubble distance in megaparsecs versus time in billions of years from 0 to 50 billion years. At any given time, the Hubble distance for that time is the proper distance from our location at which a very distant galaxy would be receding from us due to the expansion of the universe at exactly the speed of light at that time. Just a reminder that we have assumed a big chill future, not a big rip. Surrounding us, or any point in the expanding universe, is an imaginary expanding Hubble sphere, containing all the galaxies that are receding from us at less than the speed of light at that time. The Hubble sphere is the locus of points in space that are receding from us presently at exactly the speed of light. The Hubble sphere lies within our observable universe and is expanding in time as the universe expands, for a flat universe and constant dark energy density. The Hubble surface is receding away from us. The Hubble distance now is 4430 megaparsecs. This is the dark blue square on the blue curve. The Hubble distance increases with time for the restrictions we have set. For constant dark energy density, the Hubble distance will tend to a fixed positive value at infinite scale factor and time. This Hubble distance will tend to 5340 megaparsecs during exponential expansion if dark energy density is constant and the current cosmological parameters are correct. The Hubble distance equaled 3080 megaparsecs at the inflection time of 7.63 billion years, 6.14 billion years ago. This is the red dot on the blue curve. Take a galaxy located at the Hubble distance at the inflection time. The dashed red line shows the galaxy's proper distance from us at later times, always beyond the Hubble surface. Receding from us at faster than the speed of light due to accelerated expansion. Take a galaxy located at the Hubble distance at a time before the inflection time. Its recession speed from us is the speed of light at that time, but will soon thereafter be less than the speed of light because expansion is decelerating. Take a galaxy located at the Hubble distance at a time after the inflection time. Its recession speed from us is the speed of light at that time, but will soon thereafter be greater than the speed of light because expansion is accelerating. For a distant galaxy closer to us than the Hubble distance at the inflection time, 3080 megaparsecs, so closer to us than that, there is a larger scale factor at which that galaxy crosses beyond the Hubble surface, overtakes the Hubble surface. The green curve is 500 megaparsecs from us at the inflection time. 500 is less than 3080. And it will cross the Hubble distance around 46 billion years after the Big Bang. The purple dot-dashed curve is the Hubble distance divided by the scale factor for that time. For any given time, a point on this curve tells you how far from us now a galaxy must be to be at the Hubble distance at the given time. You might have to give this some thought. Galaxies closer to us today than today's Hubble distance will pass beyond the Hubble surface in the future exponential expansion. We will look at this another way shortly. Distant galaxies are moving away from us, but the Hubble distance is also increasing with time. We need some math to understand how this works. After cosmic inflation, early in the universe, expansion was strongly decelerating, dominated by radiation. The deceleration term, Q, was 1. The Hubble surface and the cosmic particle horizon coincided, and both receded at twice the speed of light. This is the narrow spike at the upper left of the graph. After 300 million years, matter slowed the Hubble surface recession speed down to 1.5 times the speed of light, where it remained for a billion years before the dark energy further slowed it. In our exponentially expanding Big Chill future, Q will approach -1, the Hubble surface will approach a constant maximum size, and its recession speed will approach 0. The situation would be different for the Big Rip case. Q was 0 at the inflection time 6.14 billion years ago, when expansion changed from decelerating to accelerating. The Hubble distance was 3080 megaparsecs at that time. The Hubble surface recession speed was exactly the speed of light. This is the red dot on the curve. Before the inflection time, expansion was decelerating, galaxies' recession speeds were decreasing, and the Hubble surface was receding faster than the speed of light. Galaxies that were receding from us slightly faster than the speed of light would be overtaken by the Hubble surface receding faster than the speed of light. The galaxy would subsequently be receding from us slower than the speed of light. The galaxy would enter the Hubble sphere from beyond. After the inflection time, expansion was accelerating. Galaxies' recession speeds were and are increasing. Galaxies receding from us at an accelerating rate will overtake the Hubble surface, receding slower than the speed of light. Galaxies will subsequently be receding from us faster than the speed of light. These galaxies will exit the Hubble sphere permanently. Let's consider a galaxy that is exactly the Hubble distance away from us now, 4430 megaparsecs. The scale factor now is 1. The recession velocity is the speed of light. The scale factor will be 2 in 11.1 billion years. That galaxy will be 8860 megaparsecs from us then. The Hubble distance will be 5190 megaparsecs then, and the galaxy will be beyond the Hubble distance for that time and forever after, receding faster than the speed of light, while the Hubble distance recedes at less than the speed of light. A galaxy that crosses the Hubble distance at scale factor 2 is only 2595 megaparsecs from us now. So all the galaxies further from us than 2595 megaparsecs today will be beyond the Hubble surface in the future after scale factor 2. Distant galaxies cross beyond the Hubble distance and remain beyond the Hubble distance due to accelerating expansion. Then galaxies that were a little less distant cross over. More and more galaxies cross over as time passes. We assumed constant dark energy density with a big chill end to the universe. If dark energy density increases with scale factor, W less than -1, with a big rip end to the universe, then the Hubble distance decreases once dark energy dominates expansion. As the scale factor approaches infinity, at the finite end to the universe, the Hubble distance tends to 0. This completes the section on the Hubble distance. Part 3, Cosmic Event Horizon. It would be natural to assume that light emitted from a galaxy at or after its time crossing the Hubble surface, outbound after the inflection time, will never reach us in the future because the galaxy's recession velocity from us at any time after that time will always exceed the speed of light. This is not correct because the Hubble surface is receding from us. Presently, the Hubble recession velocity is half the speed of light. Light can reach us in the future from some locations outside the Hubble sphere. At any time after the inflection time, there is a distance beyond the Hubble distance for that time, beyond which light will never reach us in our exponentially expanding future. A cosmic event horizon. I haven't done all the calculations, but it is close to the far future Hubble distance, 5340 megaparsecs, for the cosmological parameters as known presently. The events horizon is about 5% closer than this today, but increasing with time to 5340 megaparsecs, so we will just use the far future value. Distant galaxies cross beyond 5340 megaparsecs from us, and radiation they emit afterwards can never be received by us in the future. Later, galaxies that were a little less distant cross over. More and more galaxies cross over as time passes and the universe expands. Let's consider the exponential expansion of our Big Chill future. The Hubble distance will saturate at 5340 megaparsecs, but the scale factor will continue to increase exponentially with time. When will a galaxy that is 100 megaparsecs from us today pass beyond 5340 megaparsecs? 100 megaparsecs today times future scale factor A of t sub 1 equal 5340 megaparsecs in the future, when the scale factor equals 5340 divided by 100 equals 53. And that happens 68 billion years from now. Galaxies that are 100 megaparsecs from us today, 130 times Andromeda's distance, will pass 5340 megaparsecs in about 68 billion years. Any light they emit after that time will never be received at the Milky Way, but their old light will. When our universe is 10 times its current age, all galaxies beyond our Milky Way Andromeda local group will have passed the Hubble surface and the event horizon, and we will never see their new light thereafter. In our distant Big Chill future, we will eventually see far fewer galaxies beyond our Milky Way Andromeda local group in visible light, and then none. We will continue to see galaxies' old light for hundreds of billions of years to come, though that radiation will be dimmer and highly redshifted due to expansion, the increased scale factor. So a time will come when those galaxies are no longer visible to our eyes, and a later time will come when those galaxies' light is no longer detectable by infrared telescopes. But we will continue to see Milky Way Andromeda stars until they stop shining. This completes the section on the cosmic event horizon. Part 4. How ancient light reaches us now. How does ancient light reach us? Let's recap. Once cosmic inflation ended, the Hubble surface was moving outward at nearly twice the speed of light, but with recession speed decreasing over time. Expansion was decelerating due to the energy density of radiation and matter. Expansion began accelerating when the matter energy density fell to twice the constant dark energy density. At that inflection, the Hubble surface recession velocity equaled the speed of light. Afterwards, it was less than the speed of light, and it will approach zero in the infinite future of exponential expansion, and the Hubble distance saturates at 5340 megaparsecs, assuming constant dark energy density. Prior to the inflection, galaxy recession velocities were decelerating, and a distant galaxy that had been receding at the speed of light will slow to sublight. It will cross inward into the Hubble sphere. Let's go back and look at the first stars again. Let's say that some of those stars constitute galaxy A. Earlier, I said that the light horizon distance now for light emitted by the first stars as early as 50 million years after the Big Bang is about 12,200 megaparsecs within our visible horizon. So this is the proper distance now to galaxy A. The Hubble distance is 4428 megaparsecs presently. The first star's horizon distance is much larger than our present Hubble distance and the cosmic event horizon. So any light emitted now, today, by galaxy A, whose early light we see today, will never reach us in future. The scale factor 50 million years after the Big Bang was 0.0206 and the redshift was 48. The proper distance between galaxy A and our position in the universe was 251 megaparsecs, 50 million years after the Big Bang. The Hubble distance was 23.3 megaparsecs, 50 million years after the Big Bang. The proper distance between galaxy A and our position in the universe was 10 times the Hubble distance, 50 million years after the Big Bang, when starlight was emitted that we could now receive with redshift Z of 48. Galaxy A was receding from us at 10.7 times the speed of light at that time. So how did that light ever reach us with light only traveling at the speed of light? In general relativity, the path of a particle that always travels locally straight is called a geodesic, whether the spacetime is flat or curved and the universe is static or expanding. For photons of light and other massless particles always traveling at the speed of light, the path is called a null geodesic. This graph shows proper distance from us up to 2,000 megaparsecs versus time since the Big Bang up to 14 billion years. The blue square at the lower left is galaxy A with proper distance from us of 251 megaparsecs, 50 million years after the Big Bang, whose light we are just seeing now. The purple curve is the Hubble distance, increasing with time. The black dotted curve is the proper distance from us of galaxy A, increasing with time and scale factor due to expansion. Galaxy A has always been outside our Hubble sphere and always will be. And yet we see its early light. It is within our visible universe, which is larger than our Hubble sphere. Light emitted from galaxy A toward us has always traveled toward us at the speed of light relative to local space, but the points in space were receding from us with the expansion of the universe. When the light was emitted by galaxy A was receding from us at 10.7 times the speed of light. After 1 year, the light wavefront moved 9.7 light years further from us because the space where galaxy A is located moved 10.7 light years from us, and the light moved 1 light year closer to us through that space. It would be normal to conclude that this light will never reach us, but that is wrong. The proper distance from us of the light wavefront is increasing at first, but the co-moving distance, proper distance divided by scale factor, is reducing. With a little work, the proper distance from us of the light wavefront is the blue curve. At the left, the light wavefront is not keeping up with the position of galaxy A, drifting in the Hubble flow, but neither is it separating very fast, despite traveling at the speed of light. But follow the curve up and to the right, And over a few billion years, the light wavefront has separated quite a bit from galaxy A, even though the proper distance from us is still increasing. But at 4 billion years, the location of the light wavefront now coincides with the Hubble distance at the blue dot. The Hubble surface was moving outward at faster than the speed of light and overtook the light wavefront at a distance where space was receding from us at exactly the speed of light, and the light wavefront was traveling through space toward us at the speed of light. So briefly, the light wavefront was as far from us as it was going to get, and subsequently, its proper distance from us has decreased. And now it is reaching us, the blue diamond at the lower right. You may want to pause the video and check that you understand so far. The brown dashed curve is the recession speed from us of the point in space where the light wavefront is located at that time, with scale factor at the right, up to 10 times the speed of light. It started at 10.7 times the speed of light at the upper left. It passed through 1 times the speed of light at the brown dot at 4 billion years, when the blue curve was overtaken by the Hubble distance. And now it is 0 when the light reaches us, because space just outside our local group is not receding from us. So this starlight traveled for 13.72 billion years to reach us. For the first 4 billion years, the space it traveled through was receding from us at faster than the speed of light. For the subsequent 9.7 billion years, the space it traveled through was receding from us at slower than the speed of light. But the blue curve tells us more than just the light from the first stars. It is the curve of light reaching us now, emitted from any distant galaxy in the past. The red triangle is a galaxy with redshift z equals 10. The brown triangle is a galaxy with redshift z equals 2. The green triangle is a galaxy with redshift z equals 1. For starlight that we receive now with z greater than 1.6, emitted in the first 4 billion years, the emitting galaxy was beyond our Hubble surface at the time of emission, that is, receding faster than the speed of light, and yet the light has reached us. For starlight that we receive now with z equal 1.6, the galaxy was at our Hubble surface at the time of emission, receding at exactly the speed of light. This is the blue circle on the graph. This is the furthest proper distance from us at the time of emission for light that is reaching us now, 1780 megaparsecs. Galaxies with larger and smaller redshifts were closer to us at the time of emission. We can extend the blue curve to the origin to cover cosmic microwave background and early cosmic radiation. Though this section talked about starlight, it also applies to the CMB, gravitational waves, relativistic neutrinos, and cosmic rays. Radiation from some distant early galaxies, the CMB, and the early universe will continue to arrive at our location for our indefinite future, though at increased redshift over time. Part 5. How light reaches us in the future. The blue line in this graph is the proper distance from us of the light wavefront that reaches us when the universe is 150 billion years old. Light from the first stars will still be arriving, though with a redshift of 130,000 radio waves and very dim. The solid purple line is the Hubble distance. This saturates at 5340 megaparsecs at the upper right, as expansion is exponential and we're assuming constant dark energy density. The dotted purple horizontal line represents the event horizon at 5340 megaparsecs. Note that the blue line is beyond the Hubble distance before 38 billion years, and then crosses inside the Hubble sphere. At that crossing, the proper distance is 5320 megaparsecs, which is inside the 5340 megaparsec event horizon, and we will eventually see that light. This light spends about 30 billion years near 5320 megaparsecs away from us. The red curve is galaxies that are 100 megaparsecs away from us today. 130 times Andromeda's distance. They will pass the Hubble distance and the event horizon when the universe is 82 billion years old. Some of the light that they emit hundreds of millions of years before they cross the Hubble distance will reach us when the universe is 150 billion years old, with a redshift of about 50, so shifted to infrared. Other light that they emit immediately after crossing the Hubble distance, but before crossing the event horizon, will reach us much, much later and further redshifted. At 150 billion years, no galaxy beyond our Milky Way Andromeda local group will be visible to us anymore in the visible range, and later not even in the infrared range. But we will continue to see Milky Way Andromeda stars until they stop shining. Part 6. Proper distance and luminosity distance versus redshift. This log-log graph shows various distances for a galaxy that emitted light in the past, and the light is received by us now with cosmological redshift z, which is the horizontal axis, ranging from 0.01 at the left to 100 at the right. Galaxies close to us are at the lower left. Far from us and long ago is to the right. The distances are all divided by the present Hubble distance, which is 4430 megaparsecs, and the vertical axis ranges from 0.001 at the bottom to 1000 at the top. Our universe is flat or nearly flat, zero curvature. The black dashed horizontal line represents the present Hubble distance. The black dotted curve represents the Hubble distance at the time the light was emitted, smaller in the past. The blue curve is the present proper distance now for the galaxy that emitted the light in the past. For z greater than 1.47, the present proper distance is larger than the Hubble distance. For z greater than 2, the present proper distance is larger than 5340 megaparsecs, and we will never see light emitted after now. The green curve is the proper distance at the time the light was emitted. The curve has a maximum at z equal 1.6, 0.405 times the present Hubble distance, or 1790 megaparsecs. This is the point where the green curve and the black dotted curve cross. For z greater than 1.6, the light was emitted by the galaxy when its proper distance from us at that time was larger than the Hubble distance at that time. But the light has reached us. The green curve is also the angular diameter distance, how far the galaxy seems from the angular diameter measurement of a standard ruler, such as the diameter of the largest galaxy in a supercluster. The galaxy is gravitationally bound, so its diameter is not expanding with the expansion of the universe. For z greater than 1.6, our observed angular diameter for a large distant galaxy increases with z and the galaxy's proper distance from us. The galaxy appears a little larger due to the expansion of the universe. This helps astronomers, but galaxies are not great standard rulers. The red curve is the luminosity distance, how far the galaxy seems from its luminosity and the flux we observe. The luminosity distance is 1 plus z times the present proper distance, and the light is dimmer than simply by distance due to the expansion of the universe. Observing distant early galaxies requires powerful telescopes able to image in the infrared, such as the James Webb Space Telescope. If the first stars began at z equal 50, their luminosity distance is 51 times their present proper distance from us, and their angular diameter distance is 0.02 times their present proper distance from us. The starlight is redshifted by a factor of 50, so infrared. Those first stars are 2,600 times dimmer, and the angular diameter of those galaxies is 51 times larger than if the universe had always been at the present scale factor, and the first stars and galaxies were just like today's stars and galaxies, which is probably false. I hope this information has been useful to you.